Hello everybody. In this video, we will talk about keto-enol tautomerizations. So what is keto-enol tautomerizations? So if you notice, the structure to the left it has the exact same CH2COH, and on the right side, it has the exact same CH2COH, but both of the structure differ on the hydrogens. So here, hydrogen is connected to the carbon atom to the left. And to be precise, what carbon atom we call this is our alpha carbon atom. But here, the hydrogen is connected to the OH. So you notice OH is a functional group. And what is the functional group? OH functional group is called, that's our alcohol. So we write our alcohol as O, like methanol, propanol, butanol, pentanol, and so on. And this OH group is on a double bond, on a carbon atom containing the double bond. And we know what we call molecule containing double bonds. These are alkenes, ENE. So this class of compound called enol. And enol is basically a different version of the compound that is keto. So keto in general, more stable unless there is specific scenario. So in general, ketones are more stable. So that's why you see the equilibrium is more biased to the left sides. So if you have a solution, usually this one gonna be almost 99.9%. This one would be 0.1%. But the compound do exist where you're gonna have a mixture of keto and enol version of this compound. So this is, in general, keto is more stable. I could draw the another versions here, benzene ring. So I will draw on this side. So if we have something like this, benzene ring, OH, and you notice all of these gonna have hydrogens. This is the locations of alpha going to be. I'm just gonna use this side. This side is also fine, but since we draw the double bond here, I will use this as a guideline. Okay, so we can have something like this. So this is gonna be enol because the OH group is here. The OH group is on top of a double bond, so that's why it's enol. What would be the corresponding keto version of this molecule? The corresponding keto version of this molecule would be where hydrogen from OH moved to the alpha carbon atoms. Okay, and the double bond is gonna move to the CO bond. And now you have hydrogen, the blue hydrogen is there and the red hydrogen is already theirs. So this is the keto version of the same compound. Okay, so in this particular scenario, the enol version is gonna be more stable because this is a property of benzene ring. Benzene ring likes to stay as benzene ring. So here you are losing its aromaticity, So this is an idea from the benzene chapters. It's benzene ring likes to stay as benzene ring. Okay, so here it wants to stay as benzene ring. So I think I should put this one here. Benzene ring likes to stay as benzene ring. Okay. All right. Okay, so this is probably one of those few scenarios where enol would be a little bit, not a little bit, by a lot more stable than the keto version. But in general, keto version is going to be more stable. So maybe you can practice a couple of more examples. Let's say you want to draw the enol version of, so let's figure out what is it. Is it keto or enol? Well, obviously this is enol, and because the OH group is on top of a double bond, so that's our enol. Can you draw the keto version of the molecule? So here is how you're going to do this. Draw the exact same canonical structure with C and O, and move the H from here. So move the H here to this carbon atoms, and then move the double bond from here to CO bond. And that's it. So this position had a hydrogens, now it has two hydrogens, right? So that's how you can draw the keto version. So obviously, which one would be more stable? Keto version is always more stable. So in equilibrium, you're gonna have situations uh, where the equilibrium is going to be more biased towards the keto. So let's look at the conversions, how we can draw mechanistically. So we can do this conversions base catalyzed or acid catalyzed. So base catalyzed, I'll start with the base catalyzed. So we will use OH minus, base catalyzed, keto, enol, tautomerizations. I don't like to write the word tautomerization, so I'll just put conversions. Okay, so let's start here. CH2, COH. So this is our keto versions, and there is the alpha hydrogen. So this is our alpha hydrogen. So this is our alpha carbon atom, and this is our alpha hydrogens. All right, so this is our alpha hydrogens right here. So what happened if you use a base? So if you use a base like OH minus, the OH minus would abstract the proton, the alpha hydrogens. It will move the electron towards carbon atoms. So in this scenario, the equilibrium is going to be a little bit more biased to the left because OH minus is not as strong of a base, because so you got CH2 negative, C, O, H. So this, the resonance contributing structure for this one would be this, where the negative charge can be delocalized across the O negative ions. Okay, so when you have O negative ions, so O negative ions, it's gonna react with the water. So where does the water come from? So you notice here OH minus is abstracting H. So basically you're gonna make H OH water, right? So this water you just created is gonna be utilized again. It doesn't have to be green hydrogens, it could be the other side, but I'm just showing you for the purpose of it. I'm just showing you for the fun so that you can see the hydrogen from the bottom just move up to the top. CH2 double bond C, OH, and H. So this molecule here is our enol. So that's our enol. So we started with keto, and we ended up with enol just by removing alpha hydrogen. And what is the end product? What's left over? We left over with OH minus. So you notice we started with OH minus, but we got back our OH minus, so that's act as a catalyst. So that's why it's called base catalyzed, because you're using base. Okay, so simply we can do the same thing as well with acid catalyzed. I'm just gonna worry. Okay, so we can do the exact same thing with acid catalyzed as well. Okay, I'm gonna ignore all the equilibrium signs for this part to do this. CH2H. When we say acid catalyzed, that means H3O plus. Okay, so what happened when you have ton of acids? So far we know when you have a lot of acid, the oxygen lone pair loves proton, so it will abstract a proton. So that would make CH2 OH. When oxygen has 3 bonds, it should have a positive charge, and then H. And what should be our goal? Every time you have a positive charge on oxygens, we neutralize it. We can neutralize the positive charge by bringing this pi electrons. If we do that, this carbon atom will lose its octet because now it's going to have 1, 2, 3 bonds because one of the bond is gone to oxygens. So to maintain the octet, what can we do? We can bring these 2 electrons here, and this proton will be gone. Now, who would abstract that proton? Well, it turns out when you deprotonate your H3O plus, you just created water, right? So you just created water on its neutral state. So this oxygen would abstract the proton. So now you have CH2 double bond C O H H, and then we got H O H H plus. So you see, we got back our H3O plus. So we started with H3O plus, we got back our H3O plus. Okay, so that's how you can do keto enol conversion from acid or base catalyze. Okay, let's stop this video here.